Hello, everyone! In this lesson, we will delve into the solution for automobile lamp testing, particularly focusing on how to establish a coordinate system using the iterative method for accurate measurement. As a critical component of vehicles, the surface curvature and installation accuracy of automobile lamps are crucial. So, how can we use the iterative method to address the complex measurement needs of curved parts like automobile lamps? Let's uncover this step by step. Next, we will cover the following topics. By the end of this lesson, we hope you will understand the basic principles of the iterative method and be able to describe its application in automobile lamp inspection. You should also be capable of independently performing the 6-point iterative method for establishing a coordinate system on automobile lamp models and evaluating its accuracy and reliability. First, let's talk about the selection of probes. Since this part mainly involves measuring the external surface, the 3 by 40 mm probe used in previous tasks will be sufficient for the measurement requirements. In automotive lamp inspection, the key aspect is to determine whether the surface of the lamp matches the theoretical model or whether the lamp is installed correctly. By measuring the deviation between the actual surface of the workpiece and the theoretical values, we can assess whether the assembly is qualified. Next, let's explore the basic concept of the iterative method. The iterative method is a process of repeatedly calculating new values using the previous values of variables. It is mainly used when the origin of the part's coordinate system is not located on the workpiece itself, or when it is not possible to find the corresponding reference elements to determine the axis or origin. This method is typically applied to curved parts, such as blades. For fitting a coordinate system, the iterative method requires a numerical model or theoretical values, particularly vector information. It takes advantage of the high computational speed of computers, which are well suited for repetitive operations. The computer executes a set of instructions, or steps, repeatedly, and each time it executes these steps, it derives a new value from the previous one. Below is an example of the iterative method dialog box. Steps for establishing a coordinate system using the iterative method. Through the iterative method, the CMM, Coordinate Measuring Machine, software can best fit the measured data from 3 dimensions to theoretical points, or available surfaces. The elements used to establish a coordinate system with the iterative method must have theoretical values or a CAD, computer-aided design, model. Similar to the 3-2-1 method for establishing a coordinate system, the iterative method also determines the first axis by alignment, the second axis by rotation, and finally the origin's position. 1. Alignment, plane fitting feature to establish the orientation of the current working plane's normal axis. At least 3 features must be used. 2. Rotation, line fitting feature to rotate the second axis onto the feature. This step must use at least 2 features. 3. Origin, used to translate the part's origin to a specified location. All features are measured once, and PCDMIS will remeasure all input features at least once in DCC mode. For always measure all features, the user can input the maximum number of iterations in the maximum iteration count. PCDMIS will remeasure all input features at least once in DCC mode. If they are within the target radius, no further execution is needed. If any point does not hit the target area, it will be remeasured until the maximum iteration count is reached. 5. Starting label, used to specify a label. When the Always Measure All Features checkbox is selected, PCDMIS will return to the specified label when remeasuring iterative features, starting the remeasurement from this position. 6. point target radius, a tolerance zone, radius size, can be set around each point for easier manual point collection within the tolerance area. If the measurement point is outside this zone, PCDMIS will remeasure this point in DCC mode. A good tolerance selection is around 0.5 mm. If the remeasurement continues indefinitely, this value should be increased. 7. Positioning tolerance, used to enter a fitting tolerance value. PCDMIS will compare the elements forming the iterative coordinate system with their theoretical values based on this tolerance. Positioning tolerance only takes effect when the number of features used to establish the datum exceeds the minimum number, 3 for alignment, 2 for rotation, 1 for the origin. For example, if 4 features are used to fit a plane for alignment, the flatness cannot be 0, and the positioning tolerance will act as a limiting factor in this case. 8. Error label, used to define a label. When the error of an input feature exceeds the positioning tolerance in the reference direction, PCDMIS will move to this label. If no error label is provided, PCDMIS will display an error message indicating the error in each reference direction, and the user can choose to accept or cancel the execution of the part program. Establishing part coordinate systems using the iterative method typically uses the following approaches. A. 6 vector points, follows the 3-2-1 principle. B. 3 circles, spheres, follows the 3-2-1 principle. Now, let's look in detail at how the part coordinate system is established. Since the surface of the automotive lamp model is entirely curved, the conventional 3-2-1 method for establishing a coordinate system cannot be used here. In this case, the recommended method is to use the 6-point iterative method to establish the coordinate system. The specific steps are as follows. 1. Switch the measurement mode to manual mode. The default is generally manual. 2. Import the appropriate format of the automotive lamp model via File and Import. 3. Open the Automatic Fitting Point dialog and select fitting points on the model, or hold down Ctrl+Shift and click the left mouse button on the model to select the fitting points. Note, due to the clamping method, the 6th point must be measured at an angle of T1A90B0. 4. Use the shortcut Ctrl+Alt+A or go to Insert Coordinate System to create a new coordinate system. 5. Click on Iterative Method to enter the iterative method for establishing the coordinate system. Now, let's emphasize the principle of the 6-point iterative method. The first 3 vector points determine the alignment of the first axis by defining the plane, or curved surface. The vector directions of these 3 points should be approximately aligned. The 4th and 5th vector points determine the rotation to establish the second axis. The vector directions of these 2 points should be roughly aligned, and the line connecting these points must be perpendicular to the vector directions of the first 3 points. The 6th point determines the origin and should be perpendicular to the vector directions of the previous 5 points. According to the previously learned method of establishing the coordinate system using 6-point iterative method. 6. Select points 1, 2, and 3 and choose alignment 3, then click Select. 7. Select points 4 and 5 and choose rotation 2, then click Select. 8. Select point 6 and choose origin 1, then click Select. Afterward, click OK to complete the programming operation for the iterative method of establishing the coordinate system. 9. Make sure to select the appropriate point target radius to prevent the failure of the iterative method for establishing the coordinate system. Then use Ctrl+Q to run the program. Follow the program prompts to sequentially collect 6 points on the model using the control box. 10. Then, following the program's prompts, move the probe to the corresponding measurement point position. The measurement machine will automatically collect the points. 11. Once the points are collected, the iterative method for establishing the coordinate system is complete. We take actual measurements as an example, establish an iterative coordinate system, and use the positions of the points and the measurement path. First, use the A0B0 angle to measure 3 points on the side of the part. Next, raise the probe and measure 2 points at the top of the part. Finally, raise the probe again, rotate it to the correct angle, and measure 1 point at the front of the part. This completes the point selection for the coordinate system using the iterative method. Next, let's talk about the collection of point features. The specific steps are as follows. 1. Press Alt+C to switch the mode to automatic. 2. Change the probe to T1A90B90. 3. Click Insert Feature Auto Point Vector Point to insert the automatic vector point command. Select a point on the model and click Create. Set the clearance move to 20. 4. Select points evenly across the model, ensuring you avoid the clamping positions. 5. Move the cursor to the position of point 7. Press Ctrl+U, and the measuring machine will automatically measure and complete the measurement task for points 7 through 30. Next, let's take a look at the movement path of the measuring machine and the point selection for automatically measuring from point 7 to point 30. Since each vector point has a clearance move of 20 enabled, the probe will move 20 units away from the measurement direction both before and after measuring each point. Through this explanation, we've gained a deeper understanding of the basic principles and applicable scenarios of the iterative method. We've also mastered the specific steps for using the iterative method to establish a part coordinate system and learned about its practical applications in automotive lamp inspection. The iterative method provides an effective solution for the measurement challenges of curved parts, and I hope you can apply it flexibly to enhance both accuracy and efficiency of measurement. Finally, please reflect on this lesson and complete the following exercises to consolidate the knowledge you learned today and deepen your understanding. That concludes today's lesson. See you next time.